All right, this video is the rest of the review sheet for the final exam in Calculus 1. And I'm starting with problem number 16, which is using linear approximation to estimate the square root of 146. And you're going to choose a value that produces a small error. Okay, so here we got the square root of 146. And in this case, we're going to choose a value that's closest to 146, which is a perfect square. Okay, now in this case, my x value will be underneath the number underneath it, that's 146. So here I'm going to choose some value of a that's a perfect square that's closest to 146. And in this case, it will have to be 144, because 144 is a perfect square. Okay, so in this case here, my f of x would be the square root of x. And I can find out what f prime of x is going to be. That's going to be 1 over 2 square root of x. And one of the problems that I did in this review for the final, the square root of x, you take its derivative, it will be 1 over 2 square root of x. All right, from here, I'm going to find out what f of a is and what f prime of a will be. My a is 144, so I'll be evaluating f of 144. And my f of x is the square root of x, so that means the square root of 144 gives me 12. Square root of 144 gives me 12. And then f prime of a, well, f prime of a is 144 again, so I'll be evaluating f prime of 144. And that's going to be using this f prime of x notation as 1 over 2 square root of x. So it'd be 1 over 2 times the square root of 144. Now, we already determined that the square root of 144 is 12, so 1 over 2 times 12. We simplify that, it will be 1 over 24. So that's what f prime of a is when a is equal to 144. Now we're going to use that linear approximation formula and do our substitution. So that means L of x is this. F of a plus f prime of a times the quantity x minus a. So here my f of a, I found that out to be 12, plus f prime of a, that's 1 over 24, times x. Well, x, of course, that's 146, so I'll replace that x with 146. Minus a, which is 144. So here I got 12 plus 1 over 24 times 146 minus 144 would be 2. Now to find the approximate value, we use our calculator for that. So here we're going to have 12 plus, and I'm going to put 1 over 24 in parentheses as left parentheses 1 divided by 24, close parentheses, times 2. And to 3 decimal places, this will be approximately 12.083. Okay, so that would be the approximate value for the square root of 146. Okay, so that's problem number 16. In problem 17, we're going to determine whether the mean value theorem applies to the function f of x equals to e to the x on the interval from 0 to 4, from 0 to ln of 4. If so, find the points or point that's guaranteed to exist by the mean value theorem. Okay, so now we got in 17 f of x equaling to e to the x. And this is the interval we're dealing with, 0 to the natural logarithm of 4. Now, there are two things we need to ask ourselves to determine if the mean value theorem applies. One, is this function f continuous on the given interval 0, ln of 4. And of course, from 0 to ln of 4, I will always get a value for e to the x. Okay, so that answer there would be yes. And then second, is the function differentiable? On the open interval 0 to ln of 4. Well, if I take, let's say if I take the derivative of f of x equaling to e to the x. F prime of x, well, the derivative of e to the x is e to the x. And I still would get a value for that, for any value between 0 and the natural log of 4. So that means here, it too is differentiable on that open interval 0 to ln of 4. Okay, I answer yes to both of them, so that means that the mean value theorem applies. Mean value theorem applies. Excuse me. Now what I'm going to do here is find out what f of a is and f of b is. Here's a, that's 0, and your b is natural log of 4. So f of a, which will be f of 0, and my f of x is e to the x, so this will be e to the 0, which is 1. Now for f of b, b is the natural logarithm of 4, so it'll be f of ln of 4, which will be e to the ln of 4. Well, e and ln are inverses of each other. That means that's going to leave me with 4. So the property here is e to the ln of whatever is whatever. So e to the ln of 4 is 4. And now I'm going to use that mean value theorem formula where we have this f of b minus f of a divided by b minus a must be equal to f prime of c. Well, if f prime of x is that e to the x, why don't I replace that x with the c, so f prime of c would be equal to e to the c. Now let's do some substituting in this formula here. So in this case here, f of b came out to be 4. So this will be 4 minus f of a, which is 1, divided by b minus a. b is ln of 4 minus a, which is 0. That must equal to f prime of c, which is e to the c. Now 4 minus 1 would be 3, divided by ln of 4 minus 0 is ln of 4. So 3 over ln of 4 is equal to e to the c. Now since I know that e and ln are inverses of each other, what I'm going to do here is take the natural log on both sides of this equation. So here, ln of e to whatever is whatever. So ln of e to the exponent c is that exponent c. And that's just going to equal to ln of the quantity 3 divided by ln of 4. And I would not be able to go any further than this. So that is, whatever this numerical value is, that's going to be the point that is guaranteed to exist by the mean value theorem. Okay. Now, of course, you could type all this in by pressing the ln key, and then 3 divided by, and then left parentheses, ln 4, close the parentheses around the 4, close the parentheses around the ln, and close the parentheses again. That will give you that decimal value, 0.772. That's going to be the value of c that is guaranteed to exist using the mean value theorem. But you can leave it like this on the exam. All right, problem number 18. Consider the function y equal ln of the quantity 1 minus x and express the relationship between a small change in x and the corresponding change in y in the form of dy equaling the f prime of x dx. So here's what we got. Y equal the natural log of the quantity 1 minus x. And I'm going to rewrite this using f of x. So instead of y, I'm going to use f of x. That's going to be equal to ln of the quantity 1 minus x. And then f prime of x would be this. The derivative of the natural log is going to be 1 over the expression itself. So it'll be 1 over 1 minus x times, and I have to use the chain rule for the derivative of 1 minus x, which is negative 1. Excuse me. So here, if I multiply negative 1 times 1, that's negative 1 divided by 1 minus x. And then we're going to express this in the form of dy equaling to f prime of x dx. So we bring down the dy, but f prime of x is negative 1 over 1 minus x dx. And that is all that they're looking for in that problem. Okay, so that's problem number 18. All right, problem number 19 is this. We're going to express the following limits using L'Hopital's rule. Okay. So this is back in chapter 4. So in problem number 19, we have this. This part A, the limit as x approaches negative 1 of x to the 4th plus x cubed plus 2x plus 2 divided by x plus 1. Now notice if I replace the x with negative 1, I would get a 0 in the denominator. Not only that, if I replace the negative 1 in for x, put negative 1 in for x in the numerator, I'll also get a 0. So I get 0 over 0 situation, meaning I must use L'Hopital's rule by taking the derivative of the numerator and the derivative of the denominator until I'm able to do direct substitution. So I'm going to bring the limit over as x approaches negative 1. The derivative of x to the 4th, that's 4x cubed. The derivative of x cubed would be 3x squared, plus the derivative of 2, x is 2, divided by the derivative of this denominator. The derivative of x is 1. Now I'm not going to get 0 over 0 at all, which means I can't do the direct substitution by substituting each x with negative 1. So I got 4 times negative 1, that would be cubed, plus 3 times negative 1, that's squared, plus 2. Well, if I have a negative to an odd power, that's negative. So negative 1 cubed would be negative 1 times the 4 in front, that's negative 4. Negative 1 u squared, that's a plus 3. That'd be 1 times 3 would be 3, then plus 2. Negative 4 plus 3 plus 2 would give you 1. So the limit as x approaches negative 1 of x to the 4th plus x cubed plus 2x plus 2 divided by x minus 1 ends up being 1. And here we have to use L'Hopital's rule. All right, part B is a limit as x approaches, this time infinity, of 4x cubed minus 2x squared plus 6 divided by pi x cubed plus 4. And by looking at this here, by the leading term here, that's going to go to infinity. by the leading term in the denominator, that's going to go to infinity as well. So I have infinity over infinity. That means I need to use L'Hopital's rule. So let's try doing the limit as x approaches infinity. Take the derivative of 4x cubed, that's going to be 12x squared, minus the derivative of 2x squared would be 4x, divided by the derivative of the denominator. The derivative of pi x cubed, I'll pull the 3 down in front of the pi, and this will be x squared. The derivative of 4 is 0. Well, I'm still going to have infinity over infinity, as you can see here, because this is going to infinity, this is going to infinity, in both the numerator and the denominator. Again, I need to use L'Hopital's rule. So here the limit as x approaches infinity. The derivative of 12x squared, that's 24x, minus the derivative of 4x will be 4. The denominator, the derivative of 3 pi x squared, bring this 2 in front, multiplied by 3 would be 6 pi x. And again, I'm still having infinity to infinity. I mean infinity over infinity. So I need to use L'Hopital's rule again. So now you got the limit as x approaches infinity. The derivative of 24x will be 24, divided by the derivative of 6 pi x will be just 6 pi. Keep in mind pi is a constant. So I got 24 over 6 pi. Now keep in mind the limit of a constant is that constant itself. So it'll be 24 over 6 pi. And if I simplify this a bit, I can divide 6 into 24. That will go 4 times. So that means I'm going to have 4 over pi. And that would be the answer to the limit as x approaches infinity of 4x cubed minus 2x squared plus 6 divided by pi x cubed plus 4. Okay. All right, now part C. So here we're taking the limit as x approaches 0 of this, the cosecant of 6x times the sine of 7x. I know this is going to go to 0. This will go to infinity because that's the reciprocal of the sine function. The cosecant is the reciprocal of the sine function. So that's an infinity times 0. So here I need to rewrite this in a way that I will have infinity over infinity or 0 over 0 and then use L'Hopital's rule. Well, I know this. Let me bring the limit as x approaches 0. The reciprocal, the cosecant of 6x, it's actually 1 over the sine. So it'll be 1 over the sine of 6x. Then that's multiplied by the sine of 7x. So I have the limit as x approaches 0 of sine of 7x in the numerator divided by the sine of 6x in the denominator. Now in this case I have a 0 over 0 because I know the fact that the sine of 0 is 0. So 0 over 0 means I can apply L'Hopital's rule. So let's do that. Bring down the limit as x approaches 0. The derivative of sine of 7x, that's going to be the cosine of 7x, but I need to change rule to do this. The derivative of 7x will be 7. And the same thing here. The derivative of the sine of 6x is the cosine of 6x, but I need to take its inside derivative. The derivative of 6x is 6. Okay, so now we can do direct substitution because I know what the cosine of 0 is going to end up being. So this will be 7 cosine of 7 times 0 divided by 6 times the cosine of 6 times 0. 7 times 0 is 0. The cosine of 0 is 1. Same thing here. 6 times 0 is 0. Cosine of 0 is 1. So I got 6 times 1. That ends up being 7 over 6. Okay? So that's how we use L'Hopital's rule to evaluate these limits. All right, now on to number 20. Here we're going to be dealing with integrals on these last 5 problems here. In number 20, you want to determine the following indefinite integrals. So starting with part A of number 20. Here we got the integral of 2 over t squared minus 7t to the 5th dt. 2 over t squared minus 7t to the 5th dt. So what we're going to do here is just break this apart into 2 separate integrals here, since I got the minus sign in between. This will be the integral of 2 over t squared dt minus the integral of 7t to the 5th dt. And I have a constant of the 2, so I can pull the 2 out in front, so it'll be 2 times the integral of, and I'm going to do this. Pull that t squared out of that denominator and make that t to the negative 2 dt minus, now I can pull the constant of 7 on the outside. That'll be 7 times the integral of t to the 5th dt. Now we're going to use the power rule for each one of these. So the 2 that comes out, write down the 2. We increase the power by 1 and divide by that new power, so negative 2 plus 1 would be negative 1, so it would be t to the negative 1 divided by negative 1, minus, bring down to 7. Increase the power by 1, so it would be t to the 5 plus 1, or t to the 6, divided by the 6. And since it's an indefinite interval, we must use a plus c. Now 2 divided by negative 1, that's negative 2, divided by that t to the negative 1, I can put that in the denominator as t to the positive 1, or just t, minus 7 over 6, t to the 6, plus c. That's 7 over 1 times 1 over 6. So it'll be 7 6. So my final answer there would be negative 2 over t minus 7 6 t to the 6 plus c. All right, now part B looks like this. Let's say we have the integral of secant square of x minus 6 dx. Integral of secant square x minus 6 dx. Break those two integrals apart, you're going to get, break this integral apart, you'll have the integral of secant square of x dx minus 6 times the integral, and also I'm using the constant multiple rule where I can pull the 6 out in front of the integral sign, dx. Now let's go ahead and integrate each part. The integral of secant square x, this is one of your 6 trig functions here for integrals, that's tangent of x, minus 6 times the integral of dx would just be x, and then plus c, since it's an indefinite interval. Okay? So my final answer there would be tangent x minus 6x plus c. Okay? And then part C looks like this. The integral of the integral of 3 divided by 16s squared plus 16 ds. And in this case here, that denominator, I'm going to pull out the common factor, which is 16. So I'll bring over the integral of 3. In the denominator, I can pull out the 16, which is my common factor. And I'll have x squared plus 1 inside. So I have the integral of 3 divided by 16 times s squared plus 1 ds. Now the 3 and the 16, those are constants. That's like 3 over 16. I can pull that out in front of the integral sign. So it'll be 3/16 times the integral of, now I'm going to say ds, it will be in the numerator, over s squared plus 1. And then bring down the 3/16. If I take the integral of ds divided by s squared plus 1, now you're pretty much going to have to refer back to the tables that I gave in section 4.9 that deals with inverse trig functions. This will give you inverse tangent of s, and then plus c. So the integral of 3 divided by 16s s squared plus 16 ds will be 3/16 times the inverse tangent of s plus c. Okay. All right, problem 21 is this. Evaluate the integral from 8 to 2/16 of the cube root of y dy using the fundamental theorem of calculus. So with this one, we got the integral from 8 to 2/16 of the cube root of y dy. Now the cube root of y can be written in exponential form as y to the 1/3. So I have the integral of 8 from 8 to 2/16 of y to the 1/3 dy. And here I can go ahead and just integrate that by just increasing the power by 1 and dividing it by that new exponent. So if I add 1 to the 1/3, it will be y to the 4/3 divided by 4/3. And we're going from 8 to 2/16. Now, the reciprocal of 4/3 would just be 3/4. So this will be 3/4 times y to the 4/3. And we're going from 8 to 2/16. That 3/4, I'll treat that as a coefficient and just focus on the y to the 4/3 by taking the upper limit minus the lower limit. My upper limit is 2/16, so it'll be 2/16 raised to the 4/3 minus the lower limit, which is 8, so it'll be 8 to the 4/3. I'm putting in my limits in for y. Now I'm going to bring down this 3/4 and evaluate 2/16 to the 4/3 in the calculator. That would give me 1296 minus 8 to the 4/3. That would give me 16. So 1296 minus 16. So got 3/4 times 1296 minus 16. That's 1280. And if I do 1280 times 3/4, let me verify that it is 1280 times 3 divided by 4. That would give you 960. So the integral from 8 to 2/16 of the cube root of y dy ends up being 960. That represents the area bounded by the graph of the cube root of y and the x-axis from 8 to 2/16. Okay. All right, problem number 22 deals with symmetry to evaluate this integral from -1 to 1 of 8 plus x squared plus x cubed dx. Might have to refer back to section 5.4 for that video to find out what I'm talking about for symmetry. Okay, so I'm going to integrate each part here. Let me use a different color. For the integral from -1 to 1 of 8 dx plus the integral from -1 to 1 of x dx plus the integral from -1 to 1 of x squared dx plus the integral from -1 to 1 of x cubed dx. Now I'm going to determine whether each one of them is even or odd. Like for the 8, that's the same as saying 8x to the 0 power, which is even because the exponent on the x is even. For the x, that's x to the 1, that's odd. For x squared, that's an even exponent, that's going to be even, and x cubed. That's 2 is odd because of the exponent of 3. There's a rule that says if you take the integral from -a to a of some f of x function and it's even, it'll be 2 times the integral from 0 to a of f of x dx. For the odd, for it being odd, it would be the integral from 0 to, no, it'd just be 0. Because if you got the integral from -a to a of the function f of x and it's odd, then that means it's automatically going to be 0. This will be 2 times for the integral from -1 to 1 of 8 dx, that's even, so it'll be 2 times the integral from 0 to 1 of 8 dx. Plus, since our exponent on the x is odd, this integral will be 0, plus this is even right here, so that means the integral from 0, actually 2 times, since it's even, is 2 times the integral from 0 to 1 of x squared dx. This last one has an odd exponent, so that's going to be 0 here for that integral. Again, refer to that video for section 5.4. Bring this 2 down. Take the integral of 8 dx, that's just going to give you 8x, plus, that's 0, and then 2 times the integral of x squared dx would just be x cubed over 3. And both of these are going from 0 to 1. Now let me simplify this. 2 times 8x is 16x, plus 2 over 3 x cubed. This is going from 0 to 1. Now let's simplify this by doing the upper limit minus the lower limit. So here I'm going to have 16 times x, which is 1, plus 2 thirds times x, which is 1, and that's cube, minus the lower limit, which is 0, so it'll be 16 times 0 plus 2 thirds times 0 cube. Now I already know what this is going to be. That's going to be 0, so whatever this is minus 0 will be whatever. Now we need to figure out what this part is going to be. That's 16 times 1 minus, and I'm going to put 2 thirds in parentheses, that's 2 divided by 3 times 1 cube. Well, we got a decimal, so we need to change that to a fraction, so hit the math key and number 1 for fraction. You'll get, hold up. Okay, let me see here. I need to do something here. 16 times 1, and I'm going to put that in parentheses, and then minus 2 divided by 3, close parentheses, times 1 cube. Okay, and then press the math key and number 1 for fraction. Or do I need to do this? This is 16 plus That's 1 times 2/3 is 2/3. So this is 16 2/3, and I can write that as 50 over 3. Okay. Okay, so I went ahead and did this manually. 16 times 1 is 16. 1 cubed is 1 times 2/3 is 2/3. 16 plus 2/3 will be 16 2/3. If you write it as an improper fraction, it'll be 50 over 3. 3 times 16 is 48. 48 plus 2 is 50. So my final answer for the integral from -1 to 1 of 8 plus x squared plus x cubed dx would be 50 over 3. Okay. All right, now on to problem number 23. Use a change of variables to evaluate the integral from the integral of x to the 4th times x to the 5th plus 15x, that quantities to the 4th power, dx. And for those of you who take my Calculus 1 class, the previous review sheet had x to the 15th. I had to change it to x to the 5th because you will not be able to get a appropriate du for that because we're doing integration by substitution. So here's what I'm going to do here. Let u equal to this part right here that's in the parentheses, x to the 5th plus 15. And then du will be, bring down the 5, copy the x over to the 1 less power, so it'll be 5x to the 4th, dx. Now you see why I had to change that, because you wouldn't be able to get the correct substitution. Now, what I'm going to do here is rewrite this as the integral of, and I'm going to put this x to the 5th plus 15, that quantities to the 4th, and then put x to the 4th with that dx, because you're going to see this is almost this. I can make this be x to the 4th dx by dividing both sides by 5. So I have 1/5 du, that's going to be equal to x to the 4th dx. Now I can go ahead and make the substitution. So this x to the 5th plus 15, that would be your u. X to the 4th dx, that's going to be 1/5 du. So that means I'm going to have the integral of u to the 4th times 1/5 du. And I can pull the 1/5 out of the in front of the integral sign, so it'll be 1/5 times the integral of u to the 4th du. And from here I can use that power rule to integrate u to the 4th du by increasing the power by 1 and dividing it by that new exponent. So this will be u to the 5th divided by 5, and it's going to be plus c because of the indefinite integral. So 1/5 times 1/5 will be 1 over 25. Replace the u with that x to the 5th plus 15, and that quantity is to the 5th power plus c. Okay. And finally, problem number 24 is a definite integral. So we're going to be using change of variables for this one. The integral from 0 to 2 of 2x divided by the quantity x squared plus 2, that's raised to the 3rd, dx. All right, let's see what we can do with that one. I'm going to let u be equal to what's inside the parentheses here, x squared plus 2. that would mean du will have to be 2x dx, which is exactly what I have here, 2x dx. But you know what I'm going to do here? Change my limits of integration. These are for x. I'm going to change them for u. So if x is equal to 0, that means u then will be 0 squared plus 2. That's going to end up being 2, because 0 squared is 0 plus 2, which is 2. And then for x equals 2, that means u will be equal to 2 squared plus 2. I'm using this, substituting the x with 2. 2 squared is 4. 4 plus 2 would be 6. So now my new limits of integration will be from 2 to 6. So here's what I'm going to have. The integral from 2 to 6 this time. And of course, I'm going to show you my substitution that I'm going to use here. The x squared plus 2, that is u. 2x dx is actually du. So here's what I'm going to have. Du in the numerator divided by u raised to the third power. And I'm going to rewrite this as the integral from 2 to 6 of u to the negative 3 du. I'm just pulling u to the third out of the denominator, writing it using negative exponents. And then I'm going to go ahead and integrate using the power rule by doing this. Integrate u to the negative 3 by increasing the power by 1, so be u to the negative 3 plus 1, which is negative 2, over negative 2. And we're going from 2 to 6. Here we don't need that plus c, because it's a definite integral. Let me rewrite this as negative 1 over, pull the u squared down, that would be u squared, in the denominator from 2 to 6. And then we're going to go ahead and do the upper limit minus the lower limit, because these limits are for u, so we can just go ahead and do the substitution right there. So this first piece will be negative 1 over the upper limit, that's 6 squared, minus, and then the negative of 1 divided by the lower limit, that's 2 squared. Now I got negative. 6 squared is 36, so this will be negative 1 over 36. I'm sorry. This should be a 2 down here. And then this will be 2 times this and 2 times that. I apologize for that, because I forgot the 2 down in the denominator. So that's a negative 1 over 2 u squared. And then the upper limit will be negative 1 over 2 times 6 squared, and minus negative 1 over 2 times 2 squared. Now 6 squared is 36. 36 times 2 is 72, minus a negative. 2 squared is 4. 4 times 2 would be, 4 times 2 would be 8. So I got negative 1 over 72 minus negative 1/8. That I can type in the calculator as, in this case, negative, and then left parentheses 1 divided by 72, close parentheses, minus, then left parentheses, negative 1 divided by 8, close parentheses. Then press the math key and then the fraction. You'll get 1/9 as the final answer. So in this case here, the integral from 0 to 2 of 2x divided by x squared plus 2 quantity cubed dx will end up being 1/9. That represents the area of this curve, bounded by this curve, and the x-axis from 0 to 2. Okay, so that's all of the review of the final exam for Calculus 1. Reach out to me if you have any questions about anything in this video, and wish you the very best.